So we've been doing the vertical line test to see if it was a function. Now we have the horizontal line test to see if it's one-to-one. You use the horizontal line test to see if you could, so this is about inverses. We're talking about inverses of functions in this section. And if you can take an inverse of something, then it has to pass the horizontal line test. So the inverse is a function if it hits the point at one point. Like if I look at this one, it hits it twice. So I'm not going to be able to find the inverse of that because it didn't pass the horizontal line test. Vertical line test means you're testing to see if it's a function. The horizontal line, one-to-one is what you're looking for. And then if it is one-to-one, you can find the inverse of it. We're going to actually see in this section that it's not going to be one-to-one. But if I restrict the domain on the function, then it becomes one-to-one. So when a function is not one-to-one, it doesn't mean it's a complete wash. It just means that you're going to have to restrict the domain to make it one-to-one. All right, so that's the horizontal line test. So if we look at example 3, it says, which of the graphs 1 through 4 are a relation that are functions? Which ones are functions? Which ones are functions on 1 through 4? 1 is a function because it passes the vertical line test. So if I do the vertical line right here, how many times is it going to touch the function? Yes. Yeah, so here and here that would pass. This one, 4 would be 1 because there's nowhere that I can create a line. I'm trying to find a place where it would cross twice. So 4, and that's it. So I could find the inverse of those functions, no problem. Now we want to know relations that have inverses that are functions. So now we want to use the horizontal line test. So this one's the vertical line, and this one's the horizontal. Which ones are going to have inverses? Very good. 3 would not be 1. I could find a place where it would touch. So 2, I agree. I don't think so. Yes. I can't find a place. And then 4 is also 1. No. Is 4 1? Does it pass? What about down here? If I did a horizontal line right here, right? 1, 2. It would cross twice there. And then 1, I don't see any place. So once there, no matter where I do it, doesn't seem like it's going to be a place where it crosses twice. So I would say 1 and 2. Okay, so that's how you see it graphically. Now we're going to be looking at the algebra, and this little notation right here means inverse, F inverse. When you see the negative, it's not an exponent. That means you're telling that is the inverse. That's how you notate it. So we'll do our algebra over here. We have f of x equals x divided by x plus 1. First step is going to be to substitute in y for f of x. Substitute y for f of x. Step 2 is to switch your x and your y's. Switch x and y variables. So now y becomes an x, and all my x's become y's. Step 3 is to solve for y. So we need to solve for y, and y plus 1 is in the denominator. We need to get that out of the denominator. How can we get y plus 1 out of the denominator? Really, it's a piece that goes together. Okay, if I put parentheses around it, it stays together. Y plus 1 is like a factor. How could I get that? If it just said y down there, what would you do to get y out? Exactly. We know that we can multiply this side by y plus 1. And whatever we do to one side of the equation, we do the same thing to the other side. That way those cancel. And I'm going to bring the x out front. X times y plus 1 equals y. Very good. Do distributive property. X times y plus x equals y. We're trying to solve for y. No, this next step coming up, my calculus 2 professor was so annoyed that people didn't know how to do this algebra move. You want to collect your y's together. If you're trying to solve for y, you want to have them on the same side of the equation. So I'm going to shift the xy to the right-hand side. If it's positive xy on this side, what's it going to be on the right? Very good. I'm glad that I don't have to keep showing those kinds of steps. This is the part right now. This next step that we're going to do, he was so annoyed. This is the best algebra move. I need to isolate my y. You're going to do the distributive property backwards. You're going to factor out, I have these two terms together. I'm going to take out, what do they both these terms have in common? So I'm going to pull the y out then. What's left? So if I just put negative x in there, is it going to multiply back to the original right here? If I just put negative x, will it still equal this? No, if I just put negative x right here, it'd be y times negative x is negative xy. It wouldn't say y minus xy. There's two terms. That means that there's going to be two terms in the parenthesis as well. What could I put right here? Y times what gives me y? 1. So y divided by y is 1. You're dividing out a y. Okay, so y times 1 is y minus, if I put an x there, y times x is still a negative xy. There. Almost done. We have equals x. And how do I finish solving for y? So here's my, if it said 2y, pretend the parentheses is a 2. If it said 2y, how would you get y by itself? Divide by 2. So it says y times a parenthesis, I can divide by those parentheses, 1 minus x. Divide this side by 1 minus x. I'm going to draw an arrow that goes over here. Those cancel. And we get x. Whoops, let me move down a little bit. X divided by 1 minus x equals y. Does this look like the inverse? Is there anything about our answer that states that it's the inverse? No, it looks like a regular function y. We actually need to go one more step. We solved, and now we need to substitute. We use that on step 1. Substitute f inverse of x for y. Substitute f inverse of x for the y. That says that you have an inverse now. So I did. Here's my y. I substituted in the f of negative x for y, right? I substituted in for my y. So we switched them out in the beginning, and then we switch them back at the end. But we do need to make sure it says inverse. If it doesn't say inverse, then you're not telling me you found the inverse. Well, that was algebraically. That's what it looks like to find an inverse algebraically. I usually do this one last because this one. Let's do verifying first, because something that happens in verifying we use in the graphing. Yep, example 6. So you can verify whether or not you found the inverse. It would be like an algebra where you can check to see if you actually got the right solution. Well, you can verify, and this is how you verify. You do a composition like f of g of x. I'm going to take my g of x and put it in my f. And you have to do it the other way as well. You also have to do g of f of x. You have to do it both ways. There's something that you're going to get at the end of it, and then you'll know if you have the inverse or not. And the thing that you get at the end is what's part of the graph picture a certain way. So we're going to start with f of x so that we know we're starting with this function equals x cubed plus 1. Starting with f, and now we're going to substitute g into the f function. So I put a parenthesis wherever my x is. G of x is the cubed root of x minus 1. The cubed root of x minus 1. Now, some students are going to try to fake getting a final answer. And you need to be able to, I mean, this one's pretty simple, but sometimes you have to do a couple of steps to get to the final answer. So if I have to do 2 steps to get there, I expect my students to be the same way, because I need to start simplifying this. Can you see anything in here that simplifies? Exactly. I was hoping you'd recognize a cube root and being raised to the third power, they undo each other. And so we're left with x minus 1 plus 1. And I just want to go over here for a second just to show you that if I have a cubed root of x and it's being raised to the third power, I know that part of your algebra 2 because of COVID is missing. So I don't want to say it just disappears. Mathematically, what's happening is I can change this cube root into an exponent. All radicands also have an exponent. So I could say that this is x to the, here's my 1 for my x. Well, the radicand number always goes under the exponent. So that would be x to the 1/3, still being raised to the 3 power. That's why they're canceling, is because these two fractions, when I multiply them, it becomes just x. So that's why they go away. It doesn't just disappear magically. There is algebra that actually happens there. So just to make a little connection to your foundation. Now what do we got? Anything else to simplify? The ones. And so if you have found the inverse, you're always going to get this at the end. So you don't just do it one way. Now we got to go and confirm that g of f of x gets the same answer. You get x. What's the graph of x? What would the graph of just y equals x look like? Because that's what this is here. 45-degree angle line, right? Okay, here we go. We're going to confirm the next one. So we're going to start with g this time. G of x equals the cubed root of x minus 1. We're going to substitute f of x into g of x. All right, I can drop my parentheses because there's nothing on the inside happening here. So I can just say the cubed root of x cubed plus 1 minus 1. Yeah, so then you get the cube root of x cubed, and that's where they're going to cancel. We get g of f of x equals x. Yes, so you're doing compositions, which we've already done in this chapter. They're working up to it, right? Now we're actually using compositions. Okay, this tells you right here, this is how you verify. You're going to have two of them. That's how you verify. Verifying inverses. Now that makes me want to go back to the graph because y equals x is part of the inverse. You can't have it. If I would have just said, oh, draw the line y equals x, you'd be like, okay, I'll do it because you're the teacher. But we see that in our inverses, when we're verifying, we actually get the line y equals x. So if I go back to my graph, and let's see, 1, 1, 2, 2, because when y equals x, they're both the same. So I want to draw that 45-degree angle line, and it's a dotted line. All right, so step 1 is to draw y equals x. This is a mirror, and you're reflecting across this mirror. Whatever point that I pick, I can pick any point. It doesn't have to be an exact point. I'm going to start with an exact point. Let's go with this one. Let's pick 0, 1. If I pick the point 0, 1, what did we just do? What was the second step above in example 4? What was the second step? That means you're going to be able to see that in the graph as well. So we're going to switch the x and the y. We have 0, 1. So if 0, 1 is in the function, what's going to be in the inverse? 1, 0. So there's a point. Now, if I had graph paper, it would look a little bit more exact. Obviously, my y equals x line is off because they should be perpendicular to the line, and they should be equal distance on both sides. So I did not draw mine as best as I should have. Okay. And so if I just pick a point, like say right here, I just pick a point on the picture, and then I go perpendicular. So you got to make sure that to the line, it's a right angle. So Sometimes you guys have lines on yours. Sometimes the lines will match right up with your line so that you can see that it's, now here's a right angle right here. So I'm going perpendicular to the line. That's a right angle. If I'm this far away on the top, I need to be that far away on the bottom. I'm going to make a little more of a line right here so I can draw a right angle so I can see that it is a right angle that's there. So if I didn't give you any numbers on the graph at all, this is how you would do it. You would just pick a point on the picture, and then you would go however far to the mirror, and then you go that far past it, and you put a point. We also have another point over here at -1, 0 that I'm going to use. I'm going to use this one. So if -1, 0 is in the function, then 0, -1 would be in the inverse. So I've got a point up the top. Right now I'm having some points to help me sketch the graph. So I'd like one more that's down at the other end of the tail. I like to get both ends of the tail. So notice how it crossed over the mirror. But if I go perpendicular to my line, I'm lining up the lines on so that it's going with it. I don't know if you guys have those lines, but I can see it's a right angle here. So I'm this far away. I'm going to put a right angle there so I know that, yep, it's got to be perpendicular to the line. I'm that far away, so I'm going to go about that far on the other side. So what is the function doing? The function is coming in towards the mirror, and then it curves out and crosses over. So I am coming in. I come in. I have to go out a little bit, and then I'm crossing the mirror. I was just lightly sketching it. There it is. It comes in. It goes out a little bit. This point right here where it's crossing on the mirror, that would be for both of them as well, right there. They're both going to cross the mirror at the same place. So that was a good point to have right there. You could just pick all points and then find the inverse of the points and sketch it. But I want to show you both ways because sometimes you're going to have them without any numbers on the graph. And sometimes you'll have numbers. And so here we have the square root of x plus 3, and we need to find the inverse. Show that the square root has an inverse. State the restrictions. Okay, so if I just sketched this, so this is just a basic square root function, but it's not at the origin. This one's been shifted on the x or the y. It's been shifted on the x. This is with the x. Remember that even for this, the rule would be x minus h plus k, and the center here is still hk. So there's that same formula that we used with the parabola. It's going to be the same formula that we use for all of them, and it's just a basic function that you can shift around and translate, which is what 1.6 is about, translating. So you always take the opposite of the sign that you see in here because of that negative sign. We have h is part for x. This is with the x. Y is outside. So where is this one centered at? What's h? What's k? H is true, but it's not 3. It has to be the opposite of what you're thinking. So it's -3. What's the k? Could I write the function like this? What number could I put out here and it would still be the same function? 0. I could put plus 0. I could put, right? I could put plus 0 and that wouldn't change it. So this is centered at -3, 0. I just need a couple of points to sketch it out. And it's a square root, so I don't want to pick when x is negative. Oh, I could do -2. At -2, -2 plus 3 is 1, and the square root of 1 is 1. So that when x is -2, we get 1. 3 minus 1 is 2. That's not a perfect. I'm looking for perfect squares because of the square root. And then 2. What's 3 plus 2? So I need something that makes it a perfect square. 0 and 3 is 3. 1 and 3 is, so that would be a good one. The square root of 4 is 2. That's enough for me to be able to sketch out now. I just wanted to have some points that were, so it's going like this. It's that sideways, half of a sideways parabola. So does this pass the vertical line test? Yes, it's a function. Does it pass the horizontal line test? Yes, so it has an inverse. Passes the vertical line test. Therefore, it's a function. Passes the horizontal line test. Therefore, it has an inverse. And then we do need to state the restriction. It has a restriction. It's not the entire domain. Restriction is that, how do I find the domain for this? Look back at 1.2. 1.2, example A is a square root. How did we find the domain of that? Correct, because the original is at 0. So we take whatever's under the radicand and we take it and set it greater than or equal to 0, and then we solve, and we know what the restriction has to be. So we take x plus 3 is greater than or equal to 0. We get x is greater than or equal to -3. I mean, we could have looked at the picture and just said that, but I want to make sure that you can find it algebraically. Where's the domain start? It starts at -3. So the restriction is the function at -3?
So
it can, right? It would be a square bracket. And you're going from -3 to what? Example 1, parametric equations, where t is any real number. So we're going to make a table because A says find the points determined by t. So we're using t values. We have an x function, a y function. So we're just going to substitute in some values here for t. -3 plus 1, what's x going to be? -2. Go ahead and just fill this out. We're substituting in -2 for the t's. And then we get -1. And then we're going to do the same for the y values. We have -3 squared plus 2 times -3. -3 squared, let's see, it's important that it's in parentheses, because -3 times -3 is 9. 2 times -3 is -6. 9 minus 6. Yeah, watch out for that squaring the negative as well. So what we're going to have here is we're going to have when x was -2 and y is 3. We're creating xy ordered pairs. We have an equation that says y equals something of x. Now we have y in terms of x. Using the equations above, we solve for t, and then we substituted in the t value into the equation. All right, so we're going to start by doing x minus 1 squared. So I don't want to get into too much algebra in this class. I can get right to it from here, but I don't think that you guys... Can you guys quickly expand this out, or is this the method that you would use to do it? What do you think? Would you just take x minus 1 squared and FOIL it? Or do you guys go right to the answer from here? What's the answer going to be? So you know what your first term is going to be, x times x, right? X times x, x squared. The middle term is the one that students never can seem to find. And so if I look over here and I look at my middle term, it's -1x for inner, and the outer is -1x. There's always two answers that are exactly the same when you have a binomial being squared. So you always say 2, because of the two answers, times the first term times the second term. So 2 times -1 is -2 times x. -2x. See, -1x and -1x equals -2x. It would be great if we could always just go right to the answer here. But again, we're going to work with whatever we have. It's not your fault COVID came around, is it? Is it? And then we have the last term as well. So -1 squared is, -1 times -1 is +1. So however you have to do it to always get the right answer. Let me just tell you right now that if you don't understand why you're multiplying 2 times the first term times the last term, it would be better just go to the side on a scrap paper and do it out. Plus, now we have the distributive property here, 2 times x and 2 times -1. And then we just have to simplify a little bit here. We have y equals x squared. We do see that we have a negative 2x and a positive 2x that are going to cancel. And then 1 minus 2. So that means all of our ordered pairs that we have here should work with this equation. Yeah. So 4 squared is 16, minus 1 is 15. 3 squared is 9, minus 1 is 8. Perfect. All right. We're going to do the last example in the next class, but we need to talk about the graphing calculator as well because it says C graph. So there's something that you have to do. We're using the original. And the first thing that we need to do is we need to put it in parametric mode. So C graphing calculator, put into parametric mode. You won't see anything if you don't put it into parametric mode. So how do I do that? That's a mode that we're going to. That would be mode right here, the mode button. So you go to mode, and you can see that it's on function because we've always done function. Now we're going to start getting outside of algebra function. See where it's blinking on function? Right next to that is parametric, PAR. Hit enter. And then if you go and look at y equals, it's going to look different. It always said y equals up there. What's it say now? It says x of t and y of t, right? So what we're going to do is we're going to actually put in our equations that we have here, t plus 1. So if I go to the variable button, it's t now. So we're punching in these two equations right here, one for the x and then one for the y. See how it says xy, xy, xt, yt? So if I go over here, I'm punching in t plus 1. And then for y equals, I go right down below it, and I'm going to put in t squared plus 2t. So t, and then you have your square button, squared plus 2t. All right, we have both those functions in. We can go to the graph. If I go to my window, if I go into my window, we were going from, the t values were going from -3 to 3. Okay, that's what our table had. That's what they wanted us to do. So I actually want my t, min, and max to go from -3, use your negative button down bottom, negative. So our t min, the lowest number is -3, and the highest number is 3. Enter. So we want to look at the graph of exactly what they gave us. I can go back to the graph. Looks like this. Okay, so your window is probably, so go, you went to here and you put -3 to 3. Yeah, so -10, 10, -10, 10. We'll get back to this again. But what you do want to do is you probably want to put your mode back into function mode if you're doing any homework or anything like that. Now you got to remember to go back and forth between parametric and function mode. You go back to function mode. We'll pick up on parametrics in the next class because example 2 is really cool. I'll do that on Tuesday.